Hello dear students, in this video I'll continue with the 8th unit linear programming problem. Here we will see how to solve a linear programming problem using graphical method, that is the corner point method, when the feasible region is unbounded. In my previous video I have explained about solution, feasible solution, infeasible solution, optimal solution, feasible region, all these things, and we have seen how we can use the corner point method from the graphical method, which is helpful in finding the optimal solution for the given linear programming problem when the feasible region is bounded. In this video, we will see how we can find the solution for an LPP when the feasible region is unbounded. So this is the last theorem which I explained in the previous video. It says let R be the feasible region for a linear programming problem and let Z is equal to AX plus BY be the objective function. If R is bounded, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point of R. So if the feasible region is bounded or if it is closed, then the objective function Z will have both a maximum and a minimum value, and the maximum and minimum value of Z will occur at one of the corner points of this feasible region. And now moving on to unbounded feasible region. If R is unbounded, then the maximum or minimum value of the objective function may or may not exist. If it exists, then it must occur at the corner point of the feasible region. So if the feasible region is unbounded or if it is open, then the maximum or minimum value of the objective function, it may or may not exist. However, if it exists, it will occur at one of the corner points of the feasible region. And now we will see this example where the feasible region is unbounded, and we will see how to go about in solving this linear programming problem when the feasible region is unbounded. Solve the following linear programming problem graphically. Maximize Z is equal to 6x plus y, subject to the constraints 2x plus y greater than or equal to 3, y minus x greater than or equal to 0, then x greater than or equal to 0, and y greater than or equal to 0. So these are the constraints and this is the objective function. Now this is given after the mathematical formulation of the linear programming problem. Now we have to solve this graphically. So let us draw the graph and draw the scale, plot the points, all these things. And now let us take the first one as 1 and the second one as 2. Now we have to draw lines corresponding to equations 1 and 2. So the first one is 2x plus y equal to 3. Now when x is 0, then y is 3. When y is 0, x is 3 by 2, which is 1.5. Now if we plot the points 0, 3 and 1.5, 0 on this graph, and if we draw a straight line joining these 2 points, then we will get the line 2x plus y equal to 3. So this is 0, 3 and this is 1.5, 0. Now let us draw a line joining these 2 points. So this is the line corresponding to 2x plus y equal to 3. That is the first one. Moving on to the next line, y minus x greater than or equal to 0. So the second one is y minus x equal to 0. So when x is 0, y is 0. When x is 1, y is 1. So 0, 0 is the origin. This is 0, 0 and this is 1, 1. Now if we draw a straight line joining these 2 points, we will get y minus x is equal to 0. So this is the line y minus x equal to 0, and this corresponds to the second one. And now let us find the feasible region. Now the feasible region corresponding to 2x plus y, which is greater than or equal to 3. That is the first inequality is we have to substitute a point, say the origin here. If we substitute 0, 0, then we get 0 greater than or equal to 3, which is not true, which means the origin does not lie in the feasible region. The region corresponding to 2x plus y more than or equal to 3, it is this side. And the next one is y minus x, which is greater than or equal to 0. Now let us take any point, say 0, 1, and if we substitute here, now this point lies in y minus x greater than or equal to 0. So the region corresponding to y minus x greater than or equal to 0 is this part. So the feasible region is this entire, and then we have the non-negative constraints. X greater than or equal to 0 is this part, and y greater than or equal to 0 is this part. So the region which satisfies all these constraints, it is this entire region. So this is the feasible region. So here we can see that the feasible region is not closed, it is open. So this is an unbounded feasible region. Now if the feasible region is unbounded, then first we have to find the value of z at the corner points, because according to the theorem, if the given linear programming problem has an optimal solution, it will occur at one of the corner points. So let us mark the corner points. Now this is A 0, 3, and then we have the another corner point B, which is 1, 1. So here we have, let us find the value of z at the corner points. Z is equal to 6x plus y. So at A 0, 3, the value of z is 3. And the next corner point is B 1, 1. The value of z is 7. So here we can see that among these two, the maximum value is 7. So this is maximum. Now if the feasible region is unbounded and if the objective function is to maximize z, then we have to draw the region corresponding to the inequality 6x plus y greater than 7. So the next step is, if the feasible region is unbounded, then we have to find the region corresponding to 6x plus y, which is greater than this maximum value 7. So let us draw this line. When x is 0, y is 7, and y is 0, x is 7 by 6. So here we have 0, 7, and here we have 7 by 6, 0. Now let us draw a line joining these two points, so that we will be able to find the region corresponding to 6x plus y, which is greater than 7. So the line corresponding to 6x plus y equal to 7 is this line. Now we have to find the region which is corresponding to 6x plus y greater than 7. If we substitute the origin and check, we get 0 greater than 7. It is not true. So it means the origin does not lie in 6x plus y greater than 7. So the half plane corresponding to this is, it is this side, it is this part. So here this is the region. Now we say that if this region, if it does not interfere with the feasible region, then this corner point B will optimize the objective function. On the other hand, if this region interferes with the feasible region, it means the given linear programming problem does not have a solution. So here we can see that the line passing through this corner point B, it crosses the feasible region, and there are various points which is common to the feasible region and the half plane corresponding to 6x plus y greater than 7. So this linear programming problem, it does not have a solution. So here we have the result. So this is what is given in the book. Now here we can see that the line 6x plus y greater than 7 it is this part as shown in the figure. The red line representing the inequality 6x plus y greater than 7 is passing through corner point B1, 1 but lies in the feasible region. Now if this line, if it passes through the corner point and if it does not interfere with the feasible region, then this corner point will optimize the value of z. On the other hand, if this line, if it interferes with the feasible region, then the given linear programming problem has no solution. So here we have, hence the given linear programming problem has no solution and z cannot be maximized for any value of x and y. So if we have a feasible region which is unbounded, and if the objective function is to maximize z, then we have to find the region corresponding to z greater than the maximum value, and then we have to check whether it interferes or if it crosses the feasible region. If it crosses the feasible region, then the given linear programming problem has no solution and we cannot find the optimal value of z. So here we can see that z cannot be maximized for any values of x and y. So this is how we have to go about when the objective function is to maximize z. Now we will see an example where the objective function is to minimize z. Next question. Here we have another example where we can see that the feasible region is unbounded, but we are able to find an optimum value of z, that is a minimum value of z. Next question, minimize z is equal to 3x plus 5y subject to the constraints x comma y greater than or equal to 0, x plus 3y minus 3 greater than or equal to 0, x plus y minus 2 greater than or equal to 0. So this is another example. So let us rewrite the constraints as minimize z is equal to 3x plus 5y subject to the constraints x comma y greater than or equal to 0, then x plus 3y greater than or equal to 3 and x plus y greater than or equal to 2. It was given x plus 3y minus 3 greater than or equal to 0. So instead of this, we have x plus 3y greater than or equal to 3. And x plus y minus 2 greater than or equal to 0 can be written as x plus y greater than or equal to 2. Now we will draw the lines corresponding to these and find the feasible region. So let us mark this as 1 and 2. Now on a graph sheet, let us have OX, OY and let us choose an appropriate scale and mark the points. So first let us have the first line corresponding to the first inequality, x plus 3y equal to 3. Now when x is 0, y is 1, and when y is 0, x is 3. So we have 0, 1 here and we have 3, 0 here. Now if we draw a line joining 0, 1 and 3, 0, we will get the line x plus 3y equal to 3. So this is the line x plus 3y equal to 3. So this is the first one. And then the second equation is x plus y equal to 2 When x is 0, y is 2. When y is 0, x is 2. Now if we plot these 2 points and draw a straight line joining these 2 points, we will get the line corresponding to x plus y equal to 2. So this is 0, 2, and here we have 2, 0. So this is the line x plus y equal to 2. So this is the second equation. And now let us find the feasible region. X greater than 0, it is this part. Y greater than 0 is this part. So this is x and y greater than 0. Now x plus y greater than or equal to 3. If we substitute the origin and check 0, 0, 0, 0 is not more than 3. So origin does not lie in this region. So the region corresponding to x plus y greater than or equal to 3, it is this region. And then we have x plus y greater than or equal to 2. If we substitute origin and check, origin, it does not lie in the region, this part. So the region which is common to all these constraints, it is this region. So this is the feasible region. Here again we can see that the feasible region is unbounded. So here also the feasible region is unbounded. But here we have the objective function as minimize z is equal to 3x plus 5y. Now let us find the corner points and then we will see whether this given problem has got an optimal solution or not. So let us mark the corner points. This is A 3, 0, then we have B, and then we have C 0, 2. So we have 3 corner points A, B and C. Now we have to find the coordinates for B. B is the point of intersection of these two equations. So if we solve these two equations, we will be able to find the coordinates for B. So let us solve these two. All these can be done in the rough. So we have 2y equal to 1 or y is equal to half. X is equal to 2 minus half. So it is 3 by 2. So the coordinates for B is 3 by 2 comma half. So B is 3 by 2 comma half. Now let us find the value of z at each of these corner points. So here we have the corner point and z is equal to 3x plus 5y. At A 3, 0, the value of z is 9. At B 3 by 2, 1 by 2, the value of z is 9 by 2 plus 5 by 2, which is 14 by 2. This is 7. So at B 3 by 2, half, the value of z is 7. And then we have C. At C 0, 2, the value of z is 10. So among these, the least value is 7. So the minimum value of z is 7. So this is minimum. And here we can see that the feasible region is unbounded and the objective function is to minimize z. When the feasible region is unbounded and the objective function is to minimize z is equal to some function of x and y. In this case, we have to find the region corresponding to 3x plus 5y less than the minimum value. So we have to find the region corresponding to 3x plus 5y less than 7. Now let us draw the line corresponding to 3x plus 5y equal to 7. Again, all these can be done in rough. When x is 0, y is 7 by 5, it is 0.4. Then when y is 0, x is 7 by 3, it is 2.33. So if we plot these 2 points, 0, 1.4 somewhere here, and then 2.33, 0 somewhere here, 2.33, 0. Now let us draw a straight line joining these 2 points so that we will be able to find the region corresponding to 3x plus 5y less than 7. Now if we substitute the origin and check, we can see that 0, 0, if we substitute 0 is less than 7, so the origin lies in this region, 3x plus y less than 7. So the region corresponding to 3x plus 5y less than 7, it is this part. So this is the region corresponding to 3x plus 5y less than 7. Now here we can see that the region corresponding to 3x plus 5y less than 7, it passes through this corner point B 3 by 2, 1 by 2, and it does not interfere with the feasible region. So this corner point B, it minimizes Z. So if the corner point minimizes, if this line passes through the corner point without interfering the feasible region, then it means the given linear programming problem has an optimal solution, and the corresponding corner point, it will optimize or it will minimize Z in this case. So here we can see that as the inequality 3x plus 5y less than 7 passes through a corner point B3 by 2, half without interfering the feasible region. This means the corner point B minimizes Z, and the minimum value of Z is 7 when x is 3 by 2 and y is 1 by 2. So this is how we have to go about when the feasible region is unbounded. So if we have an unbounded feasible region, and if the objective function, if it is to maximize, say z is equal to ax plus by, and if we get the maximum value as m, if we get the maximum value as m, then we have to find the inequality corresponding to ax plus by greater than the maximum value, and then we have to check whether this ax plus by greater than m, whether this region interferes with the feasible region or not. If it interferes with the feasible region, it means we cannot maximize z. If it does not interfere with the feasible region, and if it passes through the corner point alone, then that corner point will maximize this objective function. On the other hand, if we are having the objective function as minimize, z is equal to say cx plus dy, and if we get the minimum value of z as, let us say, small m, then in this case we have to find the half plane corresponding to cx plus dy less than m, less than the minimum value. So we have to find the half plane corresponding to this, and we have to check whether this region interferes with the feasible region or not, whether this region crosses the feasible region or not. If it crosses, then we cannot minimize z for any values of x and y. On the other hand, if it does not cross the feasible region but it passes through a corner point alone, then that corner point will minimize z. So this is how we have to find the optimal solution when the feasible region is unbounded or if it is open. Now this question was given in the sample paper for term 2. The feasible region of the LPP, minimize z is equal to 3x plus 2y subject to the constraints 2x plus y greater than or equal to 6, x minus y greater than or equal to 0, x greater than or equal to 0, y greater than or equal to 0 is given below. So they have given the feasible region itself. This is the feasible region. We have to determine the optimal solution and we have to justify our answer. So this is the line corresponding to 2x plus y equal to 6 and this is the line x minus y equal to 0 and the feasible region they have given. Now here we can see that the feasible region is unbounded and the objective function is to minimize z. So we have to find the half plane corresponding to 3x plus 2y less than the minimum value. So for that, first let us find the value of z at the corner points. The corner points are P2, 2 and Q3, 0. So at P2, 2 the value of z is 10 and at Q3, 0 the value of z is 9. So this is the minimum value. Now we have to find the half plane corresponding to 3x plus 2y less than 9. So we have when x is 0, y is 9 by 2 and when y is 0, x is 3. So if we draw a line joining these 2 points 0, 4.5 and 3, 0, then we will get the line 3x plus 2y equal to 9. So this is the line 3x plus 2y equal to 9. Now the region corresponding to 3x plus 2y less than 9. Here we have to minimize z. We have to minimize z is equal to 3x plus 2y. Here since the feasible region is unbounded and the objective function is to minimize z, we have to find the half plane corresponding to 3x plus 2y less than the minimum value. The minimum value is 9. So the region corresponding to 3x plus 2y less than 9 is, if we substitute the origin 0, 0 and check, we get 0 less than 9. So the region corresponding to 3x plus 2y less than 9, it is this part. So here again we can see that 3x plus 2y less than 9, it passes through the corner point Q3, 0 without interfering the feasible region. So the corner point Q3, 0, it minimizes z. So here we have the result. The question was we have to find the optimal solution and we have to justify the answer. So we have found the optimal solution and this is the justification. The smallest value of z is 9. Since the feasible region is unbounded, we draw the graph 3x plus 2y less than 9. As the inequality 3x plus 2y less than 9 passes through the corner point Q3, 0 without interfering the feasible region. The corner point Q3, 0, it minimizes z and minimum value of z equal to 9. When minimum value of z is 9 when x is equal to 3 and y is equal to 0. So this is the optimal solution. So this is how we can find the optimal solution or whether a solution exists or not when the feasible region is unbounded. I hope this video was useful for you. Thank you for watching.